My name is Brad Edgeworth. I'm a systems architect, systems engineer, i.e. that means I'm in sales. However, I'm a double CCIE, and before I joined that, I worked in Cisco's advanced service organization supporting large service providers. So we're here to talk about troubleshooting BGP. We're not here to talk about troubleshooting BCP, the Barcelona Cerveza protocol. We should have done that last night. All right, so hopefully you guys are ready for an interesting session to understand how this routing protocol works. Now, if you think about it, we're here because of a conversation that happened over a napkin. Over a napkin. All of us in this room are here in a napkin. You think about the power of the internet, all over a napkin. That's pretty cool. To go ahead and get started with, we have a WebEx Teams room that you can join, ask questions during this session. I won't answer during, but I'll answer afterwards. As well as I have another one of my peers in there that will help answer questions as well. So go ahead and feel free to join that if you want. As far as the agenda, we're going to start off with getting peering issues. Because the first question that happens when you call an attack is what? I'm answering questions, but I don't hear answers. My keep alives are going out, but no responses. Has this ever worked before? So if you can't get peering up, that probably tells you you never got it to work before. So that's what we're going to walk through first is peering issues. And then after that, we're going to go through some of the common routing issues that we have. You know, missing routes, route churn, why do we have unexpected routes in the table when they shouldn't? And then we're also going to go talk about IPv6, and then we're going to talk about some of the optimizations within the Nexus platform for helping with troubleshooting. I'm one of the co-authors of the Troubleshooting BGP book, along with Vinit Jain. Again, he'll be in the Teams room to kind of help answer questions that may happen. Now, first question I have is, how many of you guys have attended one of the sessions with Vinit on this topic? Has anybody? Good, because I'm going to actually ask the question that I gave him to put into the session. So this is a little trivia question. Simple topology, 5 routers, right? And this is what my AS path looks like on my output, right? I want to make changes only on AS300 so that my output looks like the bottom in green. I cannot use the network or redistribute command. Everything else is fair game. And if somebody can guess the answer, I'll give away a free copy of the book. So I'll start off with, does anybody want to take any guesses to start with? Okay, something to think about, and we'll actually show you what the answer is a little bit later on. And I'll tell you, if you are a nerd and you want to make money off your friends at the bar, this is a great question to do that. I've made a lot of money off a lot of people. So to get started with troubleshooting of the BGP pairing issues, the first thing you have to think about is BGP really a routing protocol? What do you guys think? Is it a routing protocol? Yes? It is. But in order to troubleshoot it properly, you need to think about it as a routing application. In the fact that BGP does talk with the routing table, the RIB, but there's other components that are stacked on top of it. We have TCP as the underlying mechanism that it uses to communicate. And then on top of that, we have IP. Some people might equivalent it with a game like this, where if the underlying pieces don't work right, it will topple. In some ways, we might think of scenarios like this, where we're waiting for the lower components to be built up for BGP to work properly. So I want you to think about this as we go through the exercises of how we actually troubleshoot peering, right? How does BGP actually operate? It's more like what we have on the left. Does that make sense? I'm sending out keep alives. I don't hear any updates come back. All right. So the first thing that we're going to want to do is basic configuration. We're going to check the peering IP address, what is the remote AS of each side. If we have MD5 authentication, we want to make sure that's the correct way. What's one of the common issues that happens with MD5 when you're deploying from a template? We pull from spaces. Yep, spaces. The other one is they might put like a dash, and Microsoft might convert that dash to a hyphen. And then they have different answers on that copy paste. One of the things that's kind of helpful when you're troubleshooting peering issues is to take off the authentication to start with to see if that helps bring that session up. If it does, then what you're going to want to do is just reapply that authentication later on and then proceed forward, because half the time that is one of the components of the failed problems when you have authentication. And then EBGP multi-hop. EBGP multi-hop is used as far as when you're peering to something that is not directly connected on the peering networks. That is an external BGP communication. IBGP does not require this. What does this command do? Anybody? Raises the TTL of the packet. What is the default TTL of EBGP packets? It's 1, right? So there are some problems that we can have with that, and we'll talk about that on the next slide. But this should all be pretty much basic things. The other things you want to do is make sure you turn on logging of neighbor changes. Some of the platforms don't enable logging of neighbor changes by default. iOS does. The other thing is basic connectivity. Can you ping the remote device if you're doing EBGP, right? It's basic 101 stuff. And if you're sourcing it from anything than the peering address, when you do your ping, source it from the outbound that you're establishing that BGP session with. This should be basic stuff. And then always use a trace route as well, okay? Peering issues. Some of the problems with eBGP is that it's still possible for somebody with malicious intent to create a packet that will have the appropriate TTL and overload your box, right? Because the TTL check at that point happens at the RP, not at the line card, right? So that's a way that you can DDoS a box. So the other way, if you're just peering with loopbacks across the same thing, is you could use the command neighbor disable connected check, and that will allow the TTL to work properly and still establish that connection. Now, is there a better mechanism than the EBGP multi-hop? That is the TTL security. And because that actually sets the TTL value to a known value that should be checked upon receipt. The difference is that will actually operate on the line card as a check versus the RP. So now you have things that can process at line rate in the ASICs versus at the RP. So you're less likely to be susceptible to a DDoS attack. All right, so if you're peering normally, you'd will either use disabled connected check if you're doing loopbacks, or use TTL security. Now, how many of you guys will do a peering across the firewall, where it's not router to router? When you peer with your provider, you'll put a firewall in the middle. Is there many people that do that? Let's see. Okay. Now, one of the things you have to be careful of is some of the obvious things is building out the firewall rules, right? But some of the things that we might have with some of the older firewalls like PIX or ASA is we'll have problems because of the fact of we have option 19 set to remove on the ASA, which is needed for the MD5 authentication to work properly, right? So you need to account for that. So the ASA will strip that off by default, and there's a simple way that we can actually take care of that. The first process, we're going to create an ACL to kind of permit the BGP traffic and walk through the config. Now, when you do the actual ACL, what port does BGP use? 179. And so when you build this rule, you need to specify it for the source being on port 179 on one side, with not specifying the actual destination port, and then vice versa. Anybody want to take a guess why? Because we don't know which host is going to establish the session, right? So we want to make sure that we keep it for both directions. Then we're going to create a TCP map to allow option 19 to pass through for processing. We'll create the class map, and then we'll disable the sequence number stripping that also happens, which hurts the MD5 authentication process. So what does that look like? So here's the access list. You can kind of see where we've set the host does not have a port, and the BGP does on vice versa. Again, that goes back to you don't know which side is going to establish that session. The next portion is you're just going to build a second access list. This is for your class map, which will then fill into your policy map to allow the actual processing. We only want to disable that processing only for that BGP session for so we can still keep the other hosts protected from TCP denial of service attacks, but we still allow BGP to process. This make sense? All right, so far what I've covered makes sense to you guys? Pretty straightforward? All right, so I got a troubleshooting scenario. We're gonna walk through. I've got a live environment. We got R6, R7, and R8. They're gonna be paired with each other, right? With a simple eBGP peering. And I want you guys to kind of help walk me through how we go through the troubleshooting process. So we do a show BGP IPv4 unicast summary, and we can see that our neighbor state is an idle, right? So what are some of the things that I just went over that we should do to kind of verify it? You guys want to take a look at the config? So here we have our peering neighbor. We've got eBGP multi-hop. That's configured properly, right? And then here is the router in the middle. Basic connected routes, nothing on the interfaces as far as access list. And then R8. So what were some of the things that we said that we should do? The first thing we said is let's make sure that we could ping it, right? So let's do a ping between these two neighbors. So if I get on R8 and I do a ping 1067.1.6, that works. So the next thing we're going to want to do is do a trace route. Trace route works. All right? So the next thing we want to do is see is TCP actually accepting connections. So what's a way that we can check to see if TCP is going to accept a connection? Telnet, exactly. So let's establish a telnet session. Specify the port, and then we'll also make sure we specify the source interface. Telnet, we're able to establish a successful telnet session. I'm sorry, what? How's it learning the route? That's a great question. So let's look at the routing table on R8. And naturally, it's not letting me out. All right, so we'll go to R6 then. Subnet's not in table. We can cheat and look at the Ceph table, and what do we see? It's learning it through the default route. BGP will never establish a session using default route. So again, tax first question, was this ever working right? So let's add a static route. Sorry, specific route. Go back to R8. And BGP should establish, so we'll just give it a second to bring up. And now we see what BGP is established. So sometimes it's just basically breaking down to the simple things in life, right? Making sure you have that raw connectivity check. All right. So one of the things that when you can do to check as far as TCP for connectivity is run the command show TCP brief, right? And that will show you what all connections you have that are TCP. Because if you remember, BGP requires TCP for connectivity. So in this case, this output's taken from an XR box, and we see that it shows PCB for protocol control block. Now, if you're on an iOS box, it'll be TCB. I don't know why they have to have different names for things, but it just is what it is. But the same format's what it is. Basically, what you're going to look for is the 179 ports for connections. And the key thing to focus on is what is the states. If it's set for listen, what does that tell you? You don't have a session established. So you need to dive deeper into what's going on. Now, if you do a show TCP brief, it doesn't give you the detailed information as far as what's actually happening. You could take the left-hand portion of what's either a TCB or PCB and remove brief and focus in on that specific entry of what you're looking for. Now, something that may help with processing if you have a large number of entries is add the keyword numeric to make it respond a little bit faster. And when you do that, sorry, I'm jumping ahead. So this is what happens when you run that command. You'll get a little more detailed information, such as what is the local host, the foreign host, what is the TOS, where is the TOS relevant, right? Quality of service, how do you guys use COP, control plane policing, right? All these values will help you kind of figure out what's going along with the process. The other thing is it'll show you the TTL of what's being received. Again, all relevant information of what's used to get TCP up and established, build it up underneath so you don't walk out of that apartment building and fall onto the street, right? The other thing to look at is what have you received in the queue size, right? What are the number of packets that you received? Are you receiving data that's misordered, things along that nature? Now, when you look at the TCP brief, when you look at those states, you need to look for what are their state. Have you are you in a listen? Are you established, i.e. you've made successful connection? Or has it been closed? Or are you in a close wait, which means you've made connections, but now you're waiting to close that connection and no one's acknowledged that. One thing that's important with TCP is if I say something, I'm going to say with my ear open until I hear a response, right? So that's kind of important to kind of be aware of. We'll kind of touch base some other issues with that. So generally, it's something to be cognizant of when you start looking for issues is where is TCP? All right, malformed packets. Now typically, you might see a syslog message that throws up along this when you get a malformed packet, or occasionally we've seen it with software defects. Now most people freak out and go, ooh, I've got hex on my screen, this is bad. Total platonic world reversal, cats and dogs living together. No. This is actually a good thing. There's industry standards for what those messages are. The router is actually telling you what the problem is. We just don't know how to read it. But there's a website you can go to. You take that output, you paste it in there, and it will tell you what the actual issue is, so you know how to resolve it. Okay? Unsupported capability. BGP, we talked about it. When this was developed, they had one thing in mind, IPv4. What do we put on BGP now? IPv6, L2 VPN, L3 VPN. You know, now we've got VPLS, EVPN. What's next? I don't know. Vendors keep adding more and more things into BGP. So when the session comes up, the neighbors will establish what that session capability is. And sometimes you might have problems with older neighbors that don't know what those newer capabilities are, and they don't agree, so they won't establish the session. So in that case, and this typically happens in cross-vendor relationships with one vendor that doesn't support open standards, where it's supposed to be more of a soft negotiation or misconfiguration, you can use the command neighbor don't capability negotiate. And that will stop the capability negotiation. It will just bring up for that specific address family. Now, on iOS-based platforms, this is a hidden command. What does hidden command mean? Question mark doesn't work. It won't appear. On XR and Nexus, it actually will appear. Right? So this is another way to kind of help force your way up into getting that neighbor session establishment. Just like I said earlier, one of the things for troubleshooting is to take off the password authentication. You want to get to a point where you can get established so you have a baseline to understand what's going on with the box. All right, IPv4 versus IPv6. How many of you guys are using IPv6 in your network? Not BGP, just IPv6. All right, how many of you guys are using BGP with IPv6? All right, so most of you guys, awesome. More people need to do it. I'll have a trivia question at the end about IPv6 and BGP. So there's three main attributes that are carried in the actual NLRI, Network Layer Reachability Information Update, that are truly specific to IPv4, right? And that first one is the actual prefix. What is the network you're trying to reach? The next one is the next hop attribute. And the other component is the router ID. The router ID does not have to match an IP address on the box, but it's considered a good idea so you don't confuse your operational stats. It's just a unique way to identify the box. Now, if I have a BGP router ID of 0000, what happens? It doesn't come up. The box doesn't come up. When would I have a router ID of 0000? When I have a box with only IPv6 and no IPv4 addresses. So this is one of those things that we'll have to keep into mind. So when we adapt BGP for IPv6, basically we're going to include, obviously, routes for the IPv6 networks. We're also going to add some changes to the address family for the next hop, right? So we're not going to /32, it's now /128 for the for the next hop. We need to carry the IPv6 prefixes like we talked about. And then we also need to be able to account for the link local and the global IP address for that next hop. Now, why is that relevant when we have eBGP sessions with iBGP peers? If I'm peering using link local, the neighbor behavior is you advertise off of the address of the next hop to your iBGP peer. If I give my link local address off of a different interface to a different peer, what are they going to do with it? Absolutely nothing. Because link local means nothing to them because it's on a different link. So we have to start thinking about the global IP addressing when you do your peers. Now the update can contain both. So between the two, it'll contain each other, but when it goes to an iBGP, it's only the global IPv6 address that's advertised. So we'll dive more into this later on. And the router ID still remains 4 bits because entering in a /128 adds a little bit more level of confusion. We've got a lot of routes on the internet today with the current structure. We don't need to expand that right now. Peering of the extensions. I talked about the next hop extension carrying the global IPv6 address as well as the link local. The next hop field has to increment for that. So we have 16 bytes when it's only the global address is present, and 32 when it's both, right? So we gotta accommodate for when it's both, depending upon if it's an eBGP versus an iBGP peering. The router ID, again, when no IPv4 prefixes are present, we're gonna have to hard configure the router ID. How many of you guys by default configure the router ID? How many of you guys do not? Okay, you might wanna think about changing. And how many of you guys just don't like to raise your hands? All right, there we go. I got some updates coming back. I thought I had some slow peers out there, but we're moving forward. So BGP peering, right? So for the IPv4 session, we can establish and send IPv6 routes over an IPv4 session, which is pretty cool. And the IPv6 session is pretty straightforward, business as usual. However, with XR, they like to include a lot of mechanisms to prevent yourself from shooting yourself in the foot, right? So one of those is if you're going to have, a advertisement to be received, you have to have a valid IPv6 next hop when you actually establish that IPv4 session. So what we do is we make sure that we're peering with global IPv6 addresses, right, from an iBGP perspective. Why is that? Does iBGP relations modify the next hop if it's advertised along the path? No. So again, we have to have that global address to make sure it's reachable. The other thing is we'll have to make sure, like the loopback interface, if we're pairing with a loopback interface or another source interface, it has a global IPv6 interface associated with it. One of the things that we have to make sure is IPv6 unicast routing is enabled on the platform, and that neighbor discovery does not have stale entries for the global presence. Who knows what a stale entry is with neighbor discovery? Okay. Stale entry and neighbor discovery basically means that you have not heard or communicated with that IPv6 neighbor in quite some time. It doesn't necessarily mean it's a bad thing. It just means that you need to communicate with it. So if you can't actually get connectivity to make that a non-stale IPv6 neighbor, then you've got a problem. So it's just one of those things that we have to make sure that you actually have the IPv6 global address available and reachable. Does that matter for link local? No. When we look at the open message, so here's a packet capture of an IPv6 peering for the open message. We can see the BGP identifier is in the standard 128-bit, right? 4 octets. And the capability during the negotiation is multiple protocol. I need to do a different address family. So it goes through that process for the actual open negotiation. And then when we have another type of peering issues that we kind of dive into, what happens when you have a successful connection? So now you call TAC and say, hey, this has been working fine, and all of a sudden it's died, right? This is a common thing that could happen. You have to think about, well, is your IGP involved with this, right? If it is, then you need to go troubleshoot what your IGP is. So if you're pairing off of loopbacks, why are you not able to reach your loopbacks? It's a different problem. Again, remember, we're stacked upon TCP on IP to get that basic routing and reachability. So debugs is the next step that you might go for to see how you're getting that connectivity, right? We'll talk about some other techniques besides debugs, because who likes debugs? Who likes debugs on live production boxes? Wow, you guys are you work for TAC? Just asking. So one of the things we got to look for is, in this case, is we're going to check the basic connectivity. Can we ping and things like that? But then we're going to start to see, like, what are our interface counters, right? So one of the problems with this that we've kind of seen is the interface enters into a wedge state. And basically what that means is we've got a certain amount of pipe of buffers, and we're sending more traffic into it than what the buffers can take. Now, a lot of people would say, hey, that's great, we can put QoS on that, that's fine. But actually the problem is these, on most platforms, these are the buffers that are actually received before you even get into classification and qualification for that. So whether it's transit traffic or local traffic, it hits the same buffers, right? So when you enter a wedge state, when you actually look at the actual interface, you look at the queue, and if you look here on the output, you'll see we've got an input queue of 375 and 0 on the out. But on the output, we've got a queue of 1001, which means how many actual messages do we have in the queue? But our queue is a max of 1,000. That means we have more messages to be delivered outbound than what's received. So what's a quick check to see if you've been in this state? Ping your local IP address. Not your peering, but ping the IP address of that interface. You will drop packets. All right? And when you enter this state, there's a couple different things you could do. You could increase the buffers as a temporary workaround, but ultimately what you're going to want to do is figure out what's going on with that traffic, right? So there's a way that you can do that. You can take packet captures, and we'll talk about that later on. Another method is you can run the command show buffer input interface, specify the interface ID, and then do packet. And that will give you a little bit more better understanding of what the actual traffic class is going into that. And then you could start to look at, maybe you'll apply an ACL on the bigger packets to remove the affected traffic, or go trace down that automatically by default, but at least clear that queue a little bit so that now you don't have a wedge state on your protocols. Does it make sense? How many of you guys use NetFlow today? How many of you guys actually look at NetFlow? Okay, I saw one guy who didn't use NetFlow that didn't put his hand up, he did use NetFlow. That's pretty cool. So again, this is one of those things that you can actually kind of come over, and this is not a common occurrence, but it is something just to kind of be, it deals with the traffic. You might see it with DDoS attacks as commonly one of those known occurrences within that. Now, going back to, you've got the session established. Every once in a while, it will fall down. Well, why exactly is that? Well, the first thing you'll notice is you'll get the notification sent that the hold time expired. So when the hold time expired means falls, what does that mean? Correct. I sent out a keep alive and I got it back from you guys, but in this case, I never got a keep alive back, right? They never got that keep alive. How are keep alives received in BGP? It's sent out every interval, right? 60 seconds by default, or it's at the back half of a BGP update message. So if I send you out a BGP update message, do I need to send you a keep alive in that time period? And the answer is no. That's one of the ways we keep BGP from being noisy. So in this case, when we have scenarios like this where the whole timer expires, there's one of two issues. Either the router's not generating the keep alives and sending them out on the line, or R1's not receiving them, right? Which can kind of go back to some of the other things we talked about. So the first thing we're going to want to do is do a show BGP, use the address family and the sub-address family. How many of you guys still use show IP BGP commands? Stop it. Well, let me rephrase it. How many of you guys use show IP BGP commands and use more than one operating system? Okay. So why I say stop it is show IP BGP is a backwards command. They put it in a backdoor for XR and some of the other platforms, but it should be show BGP, IPv4 or IPv6 or VPN v4, and then your address family. You get used to it, it will work on every platform, right? It's a matter of training your mind. I had to do it. It's just one of those things. So anyhow, you do a look at your neighbor statistics, and you look for the last write. And you want to look for what that time period is. So if it built the interval within what the hold time is, that's a step in the right direction, right? If it's not building it, if it says like 2 minutes or 30 minutes or 3 minutes, you've got a problem. This is where you start. Why isn't BGP building up that keep alive? If it is, then this goes back to looking at the summary command, the show BGP AFI SAFI summary. And you're going to look at the out queue and see what the out queue is and then wait a bit and then rerun that command. So what does that look like? So I've done this over a time period, and we can see that the message sent says 284 and 284. The number of packets is not increasing. This is the first sign of a problem, right? Now the other thing that we'll notice is that our output queue shows that we've got 97, and then the next iteration is 98. So the number of packets that we're generating is increasing. And then if we look at it from the timestamp, right, we're at least the interval of 1 BGP keep alive. This is not good. So the out queue is not generating the appropriate keep alive. Something's stuck in the output queue. The keep alives are not leaving R2. So what we do is when we have problems like this, we want to kind of figure out what's going on. So in this case, we might have to look at debugs or captures to kind of correlate the events, right? Now in this case, how do we go back through the process? I talked about debugs and running those online. How many of you guys have taken a packet capture for BGP across a 10 gig link before? Okay, I can personally tell you I went through a case where we had this weird update. They want us to take a packet capture. We got the TAP put in place. They get the span port in, and it only had a 100 meg buffer. It took us 3 weeks to get the capture. And when I got it, I took it to the BU, and I'm like, here it is. Now fix it. But there's some other ways that we can go through that, right? So what you want to do is you want to figure out why are they not being forwarded in a timely manner. So again, look at packet captures and debugs. How can we do this? We now have tools to take packet captures on iOS routers, right? EPC, extended packet capture. How many of you guys ever used that before? Do you like it? Thumbs up, thumbs down, sideways? It's good, right? A lot better than when I was doing what you guys do, right? It's a godsend. And it works for iOS and things along that nature. And when you start to look at the packet captures, you can then run the command to view in hex. Now at this point, you're probably thinking, what do I do? And the right answer is you need to start thinking about calling TAC. Now, how many of my guys in here use Nexus? Anybody? What's another way I can take a packet capture on Nexus? What? How do you take a packet capture on a Nexus? We have a platform, we have a tool called Ethanalyzer, which is like Wireshark that's built in. Did you guys like see a live demo of that? All right. So with Ethanalyzer, one of the first questions I get asked is what impact does this have on the system? And the answer is it has none, because it was built to be incorporated into the overall architecture. It does not capture traffic that is transit through the box. It is only capturing traffic that is to the box, right? So I have access to a Nexus box that's in a lab. And so the command is Ethanalyzer, local interface in-band. And by default, when you go to capture it, it will only be a couple of packets to start with. Now that may or may not be enough to get what you want, right? So if you wanted to, you could add the keyword BGP to kind of filter it down so you're not seeing spanning tree. Zero packets captured. That's great. So we can keep on and add into the fact of limit captured frames. And if we set a value of 0, it will continue to copy packets within BGP. Now we just have to wait for a BGP update. I'm not going to clear connections or anything else like that. But it will actually display it. Now, one of the things you notice while we're waiting is the information is kind of vague. What if you need a little bit more detailed information? You can actually, you can add the detail keyword, and now I'll show you the full detail of what's in the packet capture. This is a great tool. Now you can say, that's great, but I wasn't monitoring my session, what do I do? You can actually redirect it to a local cat file and then copy it off later on. So this is one of those cool tools that has no impact. They built it in. Works for anything that is going to the box. So Ethanalyzer, if you haven't used it, start looking at it. It's a really cool tool. All right, we're back. All right, so what happens when everything's working fine on a router and then all of a sudden it starts to flap? And it's not like it's in a sporadic time period, like the wedge state, which could happen at certain times of the day, and other times it's not, depending upon traffic patterns, but it just starts flapping. And it's in a constant period. Like, this router's been fine for 2 years, and now it's into this flapping state, right? So if we start to look at it, we get the notification received, and we start looking at the timestamps, down. And again, 3 minutes later, down, and then down. So that tells you you're able to get established and then down. Whereas before, it was in a sporadic, it just dropped, and it never came back up because you're in a wedge state, not able to send anything. What does this make one think is the problem? I'm sorry, what? What? Port density? Router convergence. That could be one thing. But normally, if you have router convergence that happens like nonstop for days because you haven't taken care of it, you might have bigger problems, right? But let's say your network's stable. What other things could this lead to? Too many prefixes being advertised. Yes, to a certain degree, and we'll dive deeper. Correct. So we talked about BGP being stacked upon TCP on top of IP. So BGP, when it sends traffic using TCP, it sets the do not fragment bit, right? And so what ends up happening, and we'll kind of walk through this, is we expect that keep alive to be in the update message, and it's never received because the update message gets so large. So let's just kind of walk through what this is. So MTU, we have this thing called TCP maximum segment size, right? And so it's based off of MTU. How do we calculate the maximum segment size, or MSS? We take whatever the actual interface MTU is, we take 20 away for the actual IP, and we take another 20 for the TCP headers, right? So within that, that gives us our value. So we've got a 1500 MTU interface, take 20 and 20, we're at 1560. So if we look at this, now we have the routes that are coming across. The maximum size is going to be 1460. We add the headers, and we put the do not fragment bit on there, which is set to 1. We can get end-to-end connectivity when the entire path is completely 1500 MTU. We get the ACK back, life is good, session stays up. Now, again, if we think about this, I kind of talked about this briefly. We have our BGP update, which is the core attribute with the NRIs, and at the last is that update message. That's great. We take the default MSS, and we put that in. Well, we have to split it into packets. Life is good. But when we actually start to think about how we have to do the fraction, that introduces problems. So one of the things we could do is you could increase your MSS size, because if you have to send multiple packets, you increase your MSS size. That allows you to have larger number of updates in a packet. That's great if your environment supports jumbo frames. How many guys use jumbo frames in your environment? Okay, that's actually a reasonable size number. The problem is when somebody puts in a new device and they forget to configure jumbo frames, and you have a lot of route churn with those updates, then you'll start dropping it, and then you'll enter into this triggered state. So we go back to this. We have jumbo frames between R3 and R4, and R1 and R2. Now, when the MSS is established, part of the process is the routers will use the MTU of the local interface, right? So if it's got 9216, that's where it does its calculations off of for the maximum segment size. And then the same thing for the other guy. So in this case, we've got a maximum segment size of 9176. We take out the 40. We should be in a good shape. The problem is we start pushing across those larger packets, it gets dropped because of the don't fragment bit, right? And then when that happens, we get no keep alives, and then R4 sends this notification that the keep alives have expired, right? So BGP includes a mechanism for path MTU discovery, and theoretically it's pretty straightforward. R1 will send its packet with the do not fragment bit set when it first kind of starts up. And then basically within the middle, the devices have a couple different options. You know, if the fragment bit is not sent, it will fragment and life is good. But if it is set, it'll set a code 3 and 4 so the device is aware of it. And then the other option is dropping the packet silently, which is kind of a bad thing, right? So one of the things that we could do is we could actually turn off path MTU discovery so that we don't have some of the problems that can occur. Now, what is the downfall for turning off path MTU discovery? It changes the MSS size from the default of, let's say we got a 1500-bit interface down to, which is set at 1460, down to 576. You're going to be guaranteed to get that packet across, but now you're putting a lot more in your headers to get the information across to get it over. So your convergence is going to take longer because you've got to process more packets. Now, does everybody kind of understand the concept of why it now starts flapping on a consecutive time basis? And the trigger is the fact of the number of updates, and you'll never get out of that recovery state because you got so many updates to send in the first place, you'll never get to keep alive. Yes, sir?
But on the other side, it should never have gotten up established. There's never a hello message.
There's never a hello message. You're correct. It's not like ISIS where they pad the MTU, but it does actually establish that they have different MTUs. It's all part of the session capability negotiation. So one of the things you can do is decrease the size of the packet. Well, again, adjusting MSS is one of the things you would do in your environment, or just make sure you have consistent MTU between your BGP peers. Now, there's a way that you can test the connectivity. And basically, you run a ping between the two sources, and you set the size, and you put the do not fragment bit. Now, have you guys ever tried to play guess the MTU in the middle game? You know, where you start with like 1400 or 1500, work your way down. It's a lot of typing. Do you guys know about the sweep command? You ever heard of the sweep command? It's a pretty cool thing. You can actually do a ping and start at one lower spectrum, and it'll go all the way up to the upper end, and you can figure out where your MTU breaks. Does anybody want to see that in work? All right. So we'll go back over here. I'll clear this out. And it's a real simple topology. Go back to R6. So what we'll do is we'll run the ping command. We want to run an extended mode. Target address 771.8. Repeat count, you only need to do it once for this. Datagram size doesn't matter, timeout doesn't matter. Extended commands, yes. Ingress ping doesn't matter. Source interface, we'll just specify. Set do not fragment, yes. We want to do verbose. Sweep size ranges, this is where we hit yes. Oh, I hit the wrong value. That's going to take a while to run. So you can start to see where it starts to drop. So it started off at the smallest minimum size and went all the way through. So what that means is right now, I've got an MTU problem that drops out at 1490. And so the way to cheat, again, small little topology, you can see where I've changed the MTU to 1490. So that's a cool tool to figure out where the smallest the largest MTU that's supported for your BGP sessions. All right, troubleshooting or route filtering. So before I get into this, I showed the BGP question, the trivia question. Anybody have any guesses what might be the solution? All right, so the hint is that one of the boxes has to be iOS. It cannot be Nexus or it cannot be an XR box. And we'll dive deeper into that. All right, missing routes. Missing routes and stale routes. What does this mean? A missing route, quite clearly, is basically you have never received the route from a peer. Seems pretty straightforward. Either it was never advertised, or you filtered it incorrectly, or you had problems with the outbound, inbound processing. A stale route is a route that shouldn't exist in a table, but still does, right? So one of the things that's different about BGP when you compare it to other routing protocols like EIGRP or OSPF or things like that is once you've got the route, I'm good. I never need to hear about it again. OSPF, every 30 minutes, it'll do a complete refresh. Same thing with ISIS, and then EIGRP. Actually, EIGRP doesn't, now that I think about it. I guess it's a vector-based thing. So the first thing that could happen is, why are you missing routes? How many of you guys have ever heard of a router being in read-only mode? Okay. What this is like a safety mechanism. And it involves when convergence, when BGP first comes up. And basically, what happens is BGP enters this state, and it says, I'm only going to accept information. I'm not going to write anything into the RIB table or anything else until I have either received a complete update from my peers to make sure what it is from all my peers, or if my BGP timer has expired for that peer. And so how does a router know when it's got all the routes from a peer? When the session first comes up, there is a last update will include what is known as an end of RIB. And that is the last of the routes being processed. It's basically a blank entry. At that point, I know I've got everything from that neighbor. And then once I've got all that information, I'll change into a read-write state, I'll enter the information in my RIB, and I'll start advertising my routes to other peers. So this is what is known as write-only mode. And again, it's one of those processes of where BGP occasionally doesn't get out of that state. So how can you actually see what mode you're in? If you run the command show BGP or show BGP process performance statistics all, if you see this information show up where it's still the same, that means you're in read-only mode, right? And generally at that point, you probably want to figure out, why haven't you fully converged? This is not a common behavior, but it's something to kind of be aware of. How many of you guys are familiar with the actual BGP processing that happens within, the route advertisements, right? So route advertisements, they're done through network statements, redistribution list, or aggregation. Default routes do not come through that. You have to use the default information originate, or you could use the neighbor information originate. So if we think about it, whatever you put for your network statement goes into your RIB. Your RIB is then processed to your lock RIB, which then goes to your next hop check. Is this route actually valid, right, before it goes on to the BGP best path? All right. So I got a question for you guys. This is a joke. So 4 BGP routers go in a bar, and they have 2 beers each. Which one drives home? The one with the most weight. All right, so that was a best path joke. All right. You can say that one for the bars too. So when we actually start to do the advertisement, right, after we've identified the best path, we're then going to go to outbound route policies, which then goes to the add/rib out, which then goes to the routes to the peers. This is all process. So when you're troubleshooting, where is the process? Is it where you receive the routes, or is it from the downstream neighbor from which you've seen access to? And then, of course, if you're receiving it, this is the traffic flow as well. The route comes in from your local peers, does the validity check, right? Is the next hop reachable, things along that nature. Any inbound route policies, from there goes your lock RIB database, next hop check again, and then your BGP path, and then installs the routes to your RIB. This is what the full process looks like, inbound, outbound, as well as locally advertised. Once you get used to this, it's pretty straightforward. So when we start talking about route advertising techniques, with iOS and Nexus, we have prefix list methods, right? We can attach a prefix list on a pure straight neighbor. We can do a filter list, which now we're checking for AS path, or we can use a route map, which then we can match in a whole wide variety of BGP path attributes and prefixes and things like that. Within iOS XR, we have route policy language. How many of you guys have used XR before? Okay. How many of you guys like RPL over route maps? I'm there with you, 2 hands in the air. It's a lot better. It's programmatic, it supports nesting. There's some other cool things which I'll show you in a little bit. So the route map behavior is kind of straightforward. You have a block of code or a sequence, right? And off of that sequence, we'll process numerically in order, 10 before 20. And then there's a conditional action of what you're going to do, but that action is based off of, is there a conditional match or not, right? If there's not a conditional match, what do? You accept everything, right? If there's not a conditional match on your block, you accept everything, and then you do what that action is. It's either permit or deny based off that sequence. And then you keep going down. So people get hung up on this process, but we'll kind of walk through some of the common problems. So like, if we look at this example here on an iOS box, right? We've got an IP prefix of OSPF to BGP, and we got the route map. We've got one block that matches the IP address, and we put that in BGP. What happens? I'll take any route that's in my class A 10/8 space, is basically what happens. I'll process it. I'll redistribute it. Life is good. Now, if I expand this, and now I want to do the same thing with my IPv4 and IPv6, so I add a second entry to that same route map, so I've got one conditional match on my IPv4, one conditional match on my IPv6. What does this do? So, anybody want to take a guess what this does? I'll take every single last route on my table and push it into BGP. I don't care if it's IPv4 or IPv6. You want to know why? Let's walk through the logic. So what ends up happening is down here, for IPv4, I don't have a conditional match. I'm going to accept it, and I'm going to push it in on that one. So anything in the address family for IPv4 is coming through on the block of code for 20. Does that make sense? And then guess what? When it comes to IPv6, I don't have a conditional match within my IPv6, so I'll push it through. Now, some people might put this in because they say, look, I want one route map to rule them all, right? But this is a bad design. Split out your route maps for your address families. It makes it a little bit simple. And this is just kind of one of those examples of knowing and thinking through how the router thinks, right? Look at it, block, is there a conditional match for my address family? And then what is the action? And if they're making modifications, do that. So iOS XR. So iOS XR, I talked about this, it's programmatic. With route maps, you have one action and then just kind of process. One of the things about XR is it's programmatic. So like every route, we put an explicit deny behind it, and then we have actions like pass, which says we'll allow you to continue, here's your ticket, and you're going to continue processing. I want you to focus in on that. XR allows you to continue processing. You could change a value or an attribute, which also says, here's your ticket, but you're going to continue processing. And then you can do a drop, which is I'm done with it, I'm going to discard you. And the last is, here's your ticket, but stop processing. So again, you can do a little bit more action and filtering within XR. So some simple XR things. A route policy to pass everything, you just give it a pass, it's done. Drop is there. Now, the question I have is the drop really needed? No, it's implicit. We put it in there because of operational staff may not know that, right? And then, again, you can do filtering of packets. Here's a logical if, then else. Now, what do you guys notice about this that's kind of cool? My network prefixes are right there in my route policy language. I don't have to go define a prefix list and then reference that in my route map like you do on iOS and Nexus. I'm calling it straight out. Now you could build prefix sets, and I'm not going to get too far into that, gives you that same logic, but this is just a brief overview of it. Now, if we go look at this, somebody configure this policy, what do you think is going to happen to a prefix like 10.1.00.24? What do you think the med's going to come out at? It's going to come out at 200 because my if ends, but then I still continue processing. So it sets 200. It's kind of a bad design. I could fix that by using an else, making it if else, or I could also fix that by using a done, which then stops the processing. So just some examples of why RPL is a little bit more programmatic and powerful. When we start to look at RPL and iOS XR, when you do an eBGP peering, by default, you will not advertise or receive any routes. Again, it's a mechanism to prevent you from shooting yourself in the foot, right? It even tells you that when you actually configure it and the actual process starts to come up. Here's a basic RPL. where you can selectively accept or deny various routes with the eBGP peer. So realistically, router BGP, neighbor, blah, 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 address family, in and out will now allow you to process and receive routes in and out. Troubleshooting of filtering, regex. Who are regex people? Okay. Do you like it? Yeah, it's an acquired taste. So the main ones that most people use is underscore, which captures the before and after. So if you just say show BGP IP4 unicast regex 300, you can catch 3,000, 3,300, 4,300,000, or even 3,050. It doesn't really matter. You use a underscore to capture a space either way. The caret will do your front and start. These are some common things. So if you look at this with our sample topology, we got a lot of routes. We use the underscore that catches anything with 300. So that 300 goes. And as well, this one down at the bottom, it starts with 100, but there's a 300 in the middle, right? And if you want to just get the routes that start with 300, you start with the caret, sorry, right there. And then if you want to, you can do brackets for in between. For my XR guys, you don't like this, you could use like if AS passes through, if originates from, it becomes a little bit more easier to work with. This is a more complex process, and this one, basically anything that starts with 1 or 300 in the AS path, right? And then it also has to start with a 3 through an 8, actually space, and then not start with a 3 through 8, sorry. When you're having route updates, this is where you start to look at doing debugs, right? You could use debug BGP IPv4 updates on your iOS boxes. You could use things like event history on Nexus platforms to kind of help with the debugging. Again, I don't like running debugs, but Nexus is better at debugs because you can actually set your debugs to a log file, which we'll get to a little bit later on. But again, when you do you'll see what's actually happening with the filter list to help you figure out where the problem is, right? Where is the processing of the route missing? iOS XR, you can turn on debug. I think this is like one of the few rare use cases I've actually done debug on XR because the fact of it has traces. Traces is built into the box, and it's like running debug nonstop without any performance hit. So it's a really great platform, but this kind of goes through what that would look like. Stale routes. This is where we talked about where you've got a route that shouldn't be there, but it is. What is that actually? You know, it could be from a black hole event, an outage, routing loop is another one. You can have problems with slow peers is the reason for why you have that. The update hasn't processed properly. The sender didn't receive the updates or didn't process the update. So to kind of show you an example of where that might be, we have a simple topology. We've actually induced a stale route, and let's just kind of walk through what that looks like. So if I jump onto route reflector 2, which is this guy here on the bottom, and I look at this route from PE1, I can see that he's receiving the route only from the top inbound route reflector, from this guy at the top, right? One path. Now, if I get onto the central route reflector, he's showing the routes being advertised from the top and bottom inbound route reflector. This path should not exist, right? Because he was showing it as being the top entry. He should never have advertised it out. So this is an example of why a stale entry might or could occur. And realistically, there's no way that you can find those easily on iOS platform. However, on the XR, you could go back to doing a show BGP trace to figure out what the events are that led to that stale route. Or on Nexus, you could use the command show BGP internal event history. An event history is a logging mechanism that actually has no impact to the Nexus platform, which is good for figuring out why you might have stale routes. If you're going to do it on an iOS box, you could filter out to the route that you're actually looking for so you don't overload your console. So if you're on an internet box, you're not pushing 600,000 plus routes to it. And then if you're doing it on XR, again, you could build it in an RPL to kind of narrow down the scope of what you're actually doing for your debug, so you aren't filtering through lines of code. So back to the trivia question. Anybody want to take any guesses? Okay. R4 is the box that has to be running iOS XE. Back to route churn. When you have route churn, basically indicates that routes are flapping in your network or going up and down. If you're connected to the internet, that's expected, right? If you're not, well, then you have to look at what's going on, right? So the first thing that people say when they have route churn, outside of checking your IGPs, is you start to look at what's going on with your actual BGP process or your CPU. So you might look at your show process CPU, and you could see something that's running fairly high, like that's 91%. So you have to define what high is. Now, when I say define what high is, does anybody see a problem with that statement? Let me give you another example. I go to a restaurant and I say I like my food spicy. What does spicy mean for me? Is that like saying Dustin's Padron pepper spicy, which has no heat? Is that saying Brad's jalapeno spicy? Or is that saying Vinet's ghost pepper spicy? So the point is when you start to look at defining high, you need a baseline of what your routers are doing. How many of you guys run monitoring graphs on CPUs and stuff like that for your routers? Okay. How many of you guys don't? Okay, you should think about doing that. That way you have a baseline, because somebody goes, this is abnormal. Well, what is normal? So you want to see what is causing the issue, right? Is it things like the BGP scanner, which is processing the amount of routes that you have going, that could be causing the problem? If you are, you might want to look at the convergence. Are you having a lot of neighbors come up and down? If you have high CPU, check your neighbor summary. If you have a lot of sessions that are not established, that are just configured, and they've been in a configured down state for a long time, think about actually putting them into a shutdown state. That way you aren't consuming those CPU cycles on those neighbors, right? A little tuning here, a little tuning there will help with that baseline. But let's assume that you've done that and you're still having high CPU. It's probably going to be that route churn is a problem. So how do you identify route churn? If you've got internet routers, there's constant churn on the internet, right? It's a lot of routes. And doing a show BGP IP4 unicast and then doing diffs is going to be a little bit complicated, right? So what we like to do is start with looking at the summary for that family, show IP BGP summary. And there's a revision table. And that revision table is very helpful because when you look at it from a time interval, you can see how fast is that revision table changing, right? And so you might want to think about that if you have multiple address families. Don't forget about IPv6. Don't forget about VPNv4 or VPNv6. It's just something that you want to take in consideration. Now, the other thing that's kind of nice is we'll also, when you look at the routing table, we'll show you how long a route's been in that table, right? So you can do a show IP route pipe inc 00:00:0 to limit down the routes that have changed in that short amount of time within seconds. And when you do that, don't focus on everything. Focus on a small subset. Try to see which ones might have the same next hop IP address, and then go chase down where they live to figure out why that's churning. And if you have access, right, chase it down further down the path into your network to figure out what's causing those networks to flap. That's one way to do this, right? So here we are, we're looking at the BGP table, and we run it again, and we can see what the version table is. We've had over 1,800 prefixes that have flapped based off of the incrementation. It's pretty straightforward. And then when I was talking about the inc 00, now you can kind of zero in, and you notice that they all have the same next hop. That's who I'll go chase down. So we have to ask ourselves, what's causing this? And just like I said earlier, don't try to boil the ocean. Go after a small subset of the problems to start with. And if you're in a VRF, if you're on a PE device, you might start with VPN v4 and you end up on a PE. Don't be afraid to take it into the VRF context. We're looking where those routes are. Maybe it's the customer router is having issues, it's bleeding over into your network, right? And this goes to show you one of the things you can do is you can say, what is the most changes routes that happen in the 6th version changes? That's another technique to figure out what's changing in your network, right? Now, one of the cool things with XR is you can actually do the version difference between the 5 and 7, and it'll kind of give you that delta. And that's a cool thing with an XR. So show BGP, AF5, SAFI version, start version, end version, and it'll give you that delta. And then some of the things that might be is like maybe you have problems with the amount of traffic that you have flowing through, right? Are you overloading the TCP on a box? Again, going back to the session establishment problems we had before. If TCP traffic is increasing, maybe there's another reason for why that's happening. Check for the different AFIs like I talked about. It's not just all IPv4, it could be IPv6. Sometimes route churn is not consistent in time. Who likes the problems that happens at 3 a.m. and you find out about it 2 days later? This is where you might want to start looking at technologies like EM, where you can say, hey, look, when you enter this triggered state, I want to collect information X, Y, Z. Have any of you guys used EM before? It's a pretty powerful tool. So in this case, what we're going to do is we're going to pull SNMP for that CPU string, and then based off of that, we'll go collect the data, and hopefully that'll give us a little bit more information to figure out what's going on with that. All right, so that's route churn. So we'll go into IPv6 fairly quickly. So this goes back to the pairing of IPv6s with the addresses. With iBGP, like I said, it's only going to be the IPv6 global addresses, not the link local, because of the fact of the loop prevention mechanism doesn't exist. eBGP, if it's between directly connected peers, it will include the link local as well as the global. I know people that will peer eBGP sessions with link local. I think that's not a good decision, because what happens if you have to change the line card? It's got a different MAC address. So just food for thought as you do your design, and just keep it simple. We look at the dissecting the next hop. Here we can see that we've got the global as well as the link local, and then we have the NLRI information for what the route prefix is. And all this is, of course, in the update message. Now, when we peer with the IPv4 session, we can establish IPv6 routes right off the gate. Now, what's the one thing that kind of comes along when we do that? We're peering the session with IPv4. What do we put for the next hop? So what we'll do is we'll prefix everything with FFF, and then we'll put the back half in IPv4. Will that forward on an IPv6 network? No. So what we end up having to do is some of the platforms won't even take that advertisement, iOS will, is you're going to want to set up a route map that modifies what that next hop is to the peering of the actual IPv6 address associated to that box. So when you use the IPv4 address family to advertise IPv6s, you'll require to add that route map to change that hop. That make sense? Okay. And then also there's all the problems like route reflectors won't even advertise it. So again, this just goes through the alternate. 6PE. How many of you guys have heard of 6PE? 6PE is the way that you can get IPv6 across an IPv4 network. Have you guys heard of BGP free core? Same concept. We put MPLS on the IPv4 network, and we use MPLS labeling. People ask me, what do you need to know in networking? I'd say, you got to know layer 2, switching. You got to know layer 3 routing, and you got to know how to tunnel. Doesn't really matter how you know what technology, you got to learn how to tunnel. In this case, we're using MPLS. So within 6PE, we also have VPE, which is for our layer 3 VPN. But realistically, this was stolen off of a Cisco website. It's kind of, yeah. But let's walk through what it actually looks like, right? So we've got some PE devices that are connected with IPv6 addresses as well as with some v4, right? And what we do is we put IPv4 in our core, and we put LDP on it. So we're now doing label exchange. And then within that, we're going to dual stack the PE so they do v4 and v6, right? And then we're going to establish BGP between the PEs. Now, the provider routers in the middle really don't have to participate in the exchange of the v6 routes, right? Because all they're worried about is they're just forwarding labels. And so what that allows us to do is then we can forward the labels. Now let's walk through how that label advertisement works. So if we think about it, the inside routers are going to advertise all of the loopbacks for how to reach this PE and that PE, which there'll be appropriate labels established for. And then what we'll do is they'll get binded from LDP perspective, and then we'll have IPv6 normal advertisement to one PE and the same thing at the other PE. And then that route is going to get advertised, and that could be over an IPv4 session, right? And then we'll advertise that label back over IPv6. Because from its perspective, its pairing link is a global IPv6 label because that's where it's coming from. And so the way that works is when the packet comes in, it does a lookup on the IPv6 prefix, grabs the label from 6PE for the destination network, stacks on the multi-protocol BGP label, and then it adds a label for forwarding to the actual PE. So then that packet then forwards to P1 only on this outer label, right? Doesn't have to know anything about IPv6, which is then forwarded to P2. P2 is going to do a lookup at its label tab, see that 6PE is actually penultimate hot pop, pops that outer label, and then forwards it on to PE2. PE2 then looks at its table, says where it's going, pops the multi-protocol BGP label, and just forwards the IPv6 packet along. And so, for the most part, the configuration is pretty much the same. The big thing is underneath the address family, we're pairing with IPv4. We're sending the MPLS label. That's the key component to the configuration. Okay. And then your output, you can actually do a show IP route for the 201. You can see it's running from the IGP. You can do a show IP route. Now here's the cool thing. See how it's got the FFF 210.10.10? I told you that wouldn't work. Well, it doesn't really matter because when it actually looks at the Ceph, it knows that it's going to use the tags of 17 and 28 to forward out. One's the inner tag, one's the outer tag. So we talked about some ways we can do debugs on the various platforms. Nexus has got a lot of enhancements, or we'll say additional tools that makes it easier for troubleshooting. The first one is you can use the command show BGP process. Within that, you'll get the router ID, you'll get the confederation ID, blah, blah, blah. But where it kind of comes into other information is it shows you address family information. Where is it learning routes? Where are routes being redistributed? Things along that nature. So this is the output, and again, some of the basic stuff to start with, but it shows you the state of where it's running. We can see the number of VRFs it might have configured for each appropriate address family. But then, if you have redistribution, it will show you where the redistribution is coming from. And that's a really cool thing to kind of figure out where your attach points are for learning your routes. Event history. Event history is one of those features that you can turn on to kind of have enhanced logging without having to do debugs, right? So it's kind of built into the architecture. Now, it's a circular log process. So depending upon what you have it configured for, depends upon the amount of information it'll retain. So you can have different buffer sizes, large, medium, small, depending upon what is going on, different events, errors, or details, right? So to start with, if you just do a show BGP update event history, this is all the information you're going to get. Now, if you go and change that from the default setting and actually increase those values, you'll start to see other information like, hey, I received a UDP update message. Other additional information as far as low-level processing. You can even go into what is happening as information enters and leaves the rib. And again, this has no performance hit on the box. I'd have no problems running this in a production environment. And so the way you do it is show BGP history detail. And again, this kind of goes through what would be basically included. You get other information as far as what is going on in the low-level processing as far as BGP walks for peers, for finding things like slow peers, things along that nature. It's a really great tool to use. Conditional debugs. One of the things you can do with debugs that's different with iOS is you could debug it to a log file. So instead of clogging up your console, you debug it to a log file. If you want to log to your console, they put some mechanisms in there, again, to prevent you from shooting your foot. You got to have a high-speed serial output on your Nexus, because by default, Nexus consoles are set for 128K, right? So they kind of put some mechanism into that. You can add additional logs for updating to your rib, your B-rib, VRFs, and again, you can choose what it is for your neighbors. It's just one of those great tools to use for troubleshooting. And then as far as with Route Policy Manager is a module that runs on the Nexus platform. And its job is processing route policies, whether it's for OSPF, BGP, things along that nature. So it handles all the logic that you'd use for filtering of routes. And so it's kind of the same way as far as the route map structure is with iOS, but again, it's for Nexus different module. Now what you can do is you can actually run commands like show system internal sysmanager service to figure out things like how often has it restarted? If you're missing routes and that thing's restarting a lot, does that show you it's a stable platform? No, call TAC. So it'll also show you when was the last time it did restart. So this is a tool that's kind of useful to kind of figure out what's going on. You can also dive deeper with understanding how things are mapped into each other. So in this case, I've got two route maps. What's in it doesn't really matter. Just know it's RM test 1 and RM test 2. And then we tie it into a peer policy, which then goes to a neighbor. So we should be associated with the appropriate RM test 2 in that. Now, when we run the show system internal RPM route map, we could show that it's actually using RM test 1, which was configured explicitly for that peer. It was able to overwrite that. So it will go through any nesting, and if there's anything that takes higher precedence, it will show you what is associated to that. So the RPM is a cool process for troubleshooting it. Now, if you want to look at the history, show system internal RPM event history, it's going to throw up a batch of line of configs. You got to remember, it's going to show you what happened first and then scroll its way up. So when you're tracing the log, you're going to start with 8 and then go to 7 and then 6 and work your way back up. Because what's on top is the most recent. Unlike if you do a show log on an iOS box. Route Policy Manager, these are just some of the commands you can run, like show tech RPM. If you have any problems with what's running on with it, show system internal. Again, this is all in the slide deck. And that's going to kind of wrap up the tools in this session. So I'm going to go back to the trivia question. How do we get the AS path removed? Anybody want to take one last guess? I don't want to see this on, well, it's already been on Twitter, but all right. So here's the hard part. How do we get rid of AS200? Is there a route map or route policy to get rid of it? No. There's no way to modify AS path, and I limited you. You can't create brand new networks. So what we're going to do is we're going to aggregate that prefix into a /16. Okay? So now we've got 192.168.0.0 colon across. Now this is going to reflect, the solution is going to reflect the current problem with BGP in the industry as a whole, deaggregators. So we can do route injection. This was a feature that was developed on iOS before the full RFC was ratified, where they said deaggregation was a bad thing. That's why it only exists on iOS boxes, not Nexus XR. But we can re-inject the smaller prefix into it. Now, one of the benefits, let me go back, that's missing on the summary only is we did not contain the as set keyword. So it doesn't include any of the AS information with it. So what we're going to do is we re-inject that network of 192.168.11/32 into it, which is then going to be received by R5 as just coming out of AS300, right? As well as we still have the summary route. So the next phase is we're going to build a route map of, is there another slide? Sorry. We filter on R5 out, we filter the aggregate, and we do a prepend. So we get the AS path to match the way we want. Kind of cool trick. If you guys want, I could show it to you live on the network, but that's the process for that. All right, so nobody got it, so I still got to give books away. So question for the day is how many IPv4 networks are on the internet today? And I jumped on a route server on Earthlink this morning, literally 20 minutes before the session. Yes? 730,000? Okay, close. 800, too high. 618. What? 618, no. I'll give it to you, you're close. It was 790,000 routes. All right, so my next question then is going to be, for the next one, how many IPv6 networks? I'm sorry, who? What? 80? You're close. 79,120. As of this morning. Congratulations.
Thanks.
So, within that, I hope you found this session informative. I hope you enjoyed it. Please fill out your survey. I'll be around to answer questions you might have afterwards. I hope you've enjoyed. I normally would say summer camp for nerds, but we'll call it winter camp for nerds. So, thank you.